Welcome to Metrology lecture series. In the present video, we will discuss the sine bar and its applications. Sine bar is a precision measuring instrument used together with slip gauges to measure or set angles accurately. In general, sine bar is used for the two applications. First one is the to measure angles very accurately. Second application is the to set or position a workpiece at a required angle with high precision. Sine bar consists of a steel bar with two rollers fixed at its ends. So in the schematic I have to observe sine bar is consisting of the steel bar along with the two rollers which are the fixed at its ends. Steel bar is made of high carbon, high chromium corrosion resistant steel. It is properly hardened, precision ground and stabilized to maintain the high accuracy. Let's see the rollers. There are the two rollers have equal and accurate diameters. They are attached at the end of the bar and the axes of the two rollers are parallel to each other. These axes are also parallel to the top surface of the sine bar. Distance between the rollers, the center to center distance between the two rollers is made very accurately and usually it is the 100 to 300. So it is available three types, 100 and 200 and the 300 mm. So when the two rollers are placed on a perfectly flat surface, then top surface of the sine bar becomes parallel to that surface. And all the parts of the sine bar are hardened and stabilized before the grinding and lapping, which ensures that sine bar will become the high strength, dimensional stability and the long-term accuracy. The working surfaces of the bar and the cylindrical surfaces of the roller are finished to a very smooth surface finish of the 0.2 microns RA. This provides the high precision and proper contact. So let's see the grades of the sine bar. So there are the two grades of the sine bar. One is the A grade sine bar and the B grade sine bar. A grade sine bar having the accuracy is 0.01 mm per meter length. Similarly, B grade sine bar is the accuracy of 0.02 mm per meter length. Next we will discuss the different types of sine bar. Sine bars are available in different designs depending on the application. There are the different types are available, but here we are discussing about the only main types of the sine bar. First one is the plain sine bar. So in the schematically you have to observe this is the plain sine bar. So it is the very simplest type. So here rollers are arranged so that the one side of their outer surface is level with the top surface of the bar. And it is the most commonly used type of the general angle measurements. So next we have to see the second type of the sine bar with hollow rollers. So in the schematic you have to observe there are the rollers are the hollow and outer diameter of the rollers is equal to the width of the sine bar. It is very useful when the width of the sine bar is included in the height calculation of the workpiece. So next one is the third one, sine bar with pins on the both of the sides. So this type has the pins are provided on the both sides and it is used when a normal sine bar is cannot be placed properly on the top surface due to the some obstruction or interruptions. Next we will discuss the adjustable sine bar. So in the adjustable sine bar, the distance between the two rollers can be adjusted accurately. It can be set to a steep angle without slip gauges touching the underside of the bar. However, the accuracy reduces slightly at very steep angles. Moreover, small holes are drilled in the sine bar which has to reduce its weights and moreover making the handles very easy. So in the schematic you have to observe. So this is the adjustable sine bar diagram. Next we will discuss the principle of sine bar. A sine bar is used to measure angles based on the sine principle. The working of a sine bar is based on the basic laws of trigonometry, especially the sine function. A sine bar has the two rollers fixed at a known distance apart. This distance between the centers of the rollers is denoted by capital L. So in the schematic you have to observe. Here capital L is the distance between the centers of the rollers. So next we have to discuss the how to set or measure a particular angle. So first one is the one roller of the sine bar is placed directly on a surface plate. Next, a suitable combination of slip gauges is placed under the second roller. So first you have to place the one roller of the sine bar on the surface plate. Next one is the second roller you have to place above the slip gauges. And the height of the slip gauges is denoted by capital H. So after that, so when this setup is made, sine bar forms a right angle triangle. So in the schematic you have to observe one roller is placed directly on the surface plate. Next, a combination of the slip gauges is placed under the second roller. So based on this setup, it is forming a one right angle triangle. So it is the right angle triangle. Then, so from this right angle triangle, so we can be written sine theta equal to the h by L. So here theta equal to the angle and h equal to the height of the slip gauges and capital L is the distance between the roller centers. So next we have to discuss the different applications of the sine bar or uses of the sine bar. So first application is the locating any work to a given angle. So here we know the theta value, angle we know, then how to locate the workpiece respected to this angle. So let's see the procedure. To set a required angle using sine bar, we first assume that the surface plate is perfectly flat and horizontal. Next, one roller of the sine bar is placed directly on the surface plate. So in the schematic you have to observe. So one roller is placed directly on the surface plate. A suitable combination of slip gauges is placed under the second roller. And let small h is the height of the slip gauges. Then sine bar is then inclined at an angle of the theta. So this is the theta is the inclination angle of the sine bar. By adjusting the height small h, we can be set the sine bar to the desired angle. So then sine theta equal to the h by L, where theta equal to the angle to be set. Small h is the height of the slip gauges combination. Capital L is the distance between the centers of the two rollers. So if the theta angle is known, we can be calculate the required height small h by using this formula. That is the small h equal to the L into sine theta. So we have to remember these two formulas. So for the calculation of the problems. After placing the correct height of the slip gauges under the one roller, the top surface of the sine bar will be inclined at the required angle theta with respect to the surface plate. For the better results, both of the rollers could also be placed on the slip gauges height of the small h and capital H respectively. So in the schematically you have to observe, for the better results, we have to place the both of the rollers on the slip gauges. Let's consider one height of the slip gauge is the small h, another height of the slip gauge is the capital H. Then sine theta will become the sine theta equal to the capital H minus small h divided by L. Next we will discuss the second application of the sine bar, checking or measuring unknown angles. So for this we have to discuss the two conditions. First one is the when component is of the very small in size. So it is the schematic representation for the procedure to measure the unknown angles when the workpiece is small in the size. So let's discuss the how to measure the unknown angle using a sine bar. So with the following steps. First one is the find the approximate angle. So first I have to measure the angle of the workpiece approximately by using a bevel protractor. Second step is the set the sine bar. Based on the approximate angle, we have to calculate the required height and place a suitable combination of slip gauges under one roller of the sine bar and keep the sine bar on the surface plate. So this is the second step. So third step is the place the component. Place the workpiece on the top surface of the sine bar. If needed, clamping should be done with the angle plate. So next step is the check with the dial gauge. Set a dial gauge at one end of the workpiece and move along its on the top surface of the component. Next, you have to observe the reading. If the dial gauge shows the variation, it means top surface of the component is not parallel to the surface plate. Then we have to adjust the height of the slip gauges until the dial gauge shows no variation. So next last step is the final condition. When the dial gauge reading remains constant throughout, then top surface of the component is perfectly parallel to the surface plate. Then angle of the component is then calculated by using the following relation. That is sine theta equal to the h by L or h equal to the L into sine inverse theta. Adjusting the slip gauges again and again to get perfect parallelism takes a lot of time. So instead of repeatability adjusting the slip gauges, we can calculate the correction in angle from the dial gauge reading. Suppose dx is the variation shown by the dial gauge, small x is the distance over which this variation is measured, and theta is the angle. So it is represented in the schematic diagram also here. Dx is the variation shown by the dial gauge and small x is the distance over which this variation is measured and theta is the angle. So if there is the variation dx over a length small x, then the corresponding angle variation is the delta theta equal to the sine inverse of dx divided by small x. So this gives the correction that must be added or subtracted from the approximate angle. The approximate angle set using the sine bar is the theta equal to the sine inverse of h divided by L. Next we will discuss the second condition. When the component is the very large in the size or the heavy size. In such cases, component is placed over the surface plate. Sine bar is placed over the component as shown in the figure. So in the schematic you have to observe that one here. Component is placed over the surface plate and sine bar is placed on the component. So now we have to measure the height of the rollers of the sine bar by using these height gauges, and let's consider the R1 or R2 are the height of the rollers. Then we have to determine the angle by the following procedure. The height of the rollers of the sine bar is measured using the vernier height gauge, and a dial test indicator is mounted on the anvil of the height gauge to make sure the measuring pressure remains the constant and accurate. So after placing the component and sine bar, then you have to measure the height of the rollers by using this vernier height gauge, and moreover a dial test indicator is mounted on the anvil of the height gauge to make sure that measuring pressure remains the constant and accurate. First the anvil of the height gauge is adjusted so that the probe of the dial test indicator shows the same reading when touching the top of the each roller of the sine bar. This ensures that the measurement is taken correctly without applying the extra force. Then the height gauge is used to take two height readings, one for each of the rollers of the sine bar. So let's consider R1 and R2 are the height of the rollers of the sine bar. Then let's consider small h is the difference between the two measurement heights. That is the small h will become the R2 minus R1. And let's consider capital L is the distance between the centers of the two rollers. Then theta equal to the sine inverse of h by L. So there is the another method also there for the measuring the angle of a large sized component. So in the schematically it is the representing. So here component is placed on the surface plate, then sine bar is placed over the component. So let's see the procedure how to measure the angle by using this setup. The component is first placed over a surface plate. A sine bar is then positioned on the top surface of the component and adjusted to an approximate angle so that the sine bar surface is almost parallel to the surface plate. Next, a dial gauge is moved along the top surface of the sine bar to check whether it is perfectly parallel to the surface plate. If the dial gauge shows any variations, it means the sine bar is not exactly parallel and needs the adjustment. in the slip gauges. So let's consider small h is the height of the slip gauge combination used under the sine bar. And let's consider dh is the variation in dial gauge reading. Capital L is the distance over which the dial gauge is moved. Then the corrected height becomes the correct height equal to the small h plus or minus dh. Then angle theta is calculated, sin theta equal to the h plus or minus dh divided by the capital L. So this is the procedure for the measurement of the angles by using the sine bar. So in the next lecture we have to discuss about the gate previous problems on the sine bar, and thank you.